Okay, so I've started recording and yeah, so I mean, I looked at the questions on Piazza. I didn't think that they were very justified doubts. I'll answer there as well. I mean, the things like I mean, for example, one of the ones is regarding the function name overriding, right? So nowhere in the specification of the problem it is written that you need to have just one CPP file and one header file, right? Where did I say that? So I don't know where this confusion is coming from. That you can have a copy of your the CPP code you are writing, and you can name them as underscore MKL or underscore BLAS. And of course, the make file will have to compile all of them, right? So, I mean, some of you already have handled these things. So that is one thing as well, because some people have completed the assignment. Sometimes I don't answer things on Piazza, not because I'm not reading it, but I don't think that, I think you should figure it out yourself. Okay. So that was one that regarding that you were having some issues regarding function name resolution. The um, So you can ask here on chat, or even you can unmute yourself and ask here if there is something conceptual which you are not getting. Okay, so because on Piazza the questions I have seen, they don't seem to me to be and I will, maybe I'll just write it there or just to clarify. So yes, so this I thought through this extension of deadline thing. So yes, so that I don't do it exactly when I release the assignment, because you, so one thing is for sure, right? So your output in subtask 2, so this is the output, means the function output which you have, the result of your program, it should remain exactly same as subtask 1. So you are not doing anything different in subtask 2 compared to what you have done in subtask 1, right? So the only thing which is changing now is going to be this runtime, right? Because I am asking you to re-implement the same functions. So you were doing matrix multiplication earlier in a sequential fashion, possibly, most probably in subtask 1. So here you either are going to use this multi-threading, which might degrade the performance of your program or might improve it, right? So we will discuss today. No, so the you can submit the I mean, I think it might be too much of a botheration of I don't know how you're organizing your code. For me, I typically just keep committing to my same Git repo, so I don't delete functions or do things like that. So if it has the pooling and other things as well, you can submit that. But I think specifically I have just asked you to parallelize or use MKL or BLAS only for the matrix multiplication operation, which is for the fully connected layer. Okay. So Shrimanti, the answer to your question, whether you submit your pooling or other things, I don't expect those implementations to change between subtask 1 and subtask 2. And in subtask 3, you must have read it already that all these functions will be used. So you will be implementing a neural network where all these multiple layers of these functions will come into picture. Okay. So in terms of the like what is, if someone is asking that why don't you give me some input matrices again and the output matrices like in subtask 1 so that we can check, I don't even understand that question, because the inputs and the output will remain same here as well, right? Because you are just doing exactly the same operation. It's only that the way you are doing your matrix multiplication, either you are calling a library function from MKL or another library function from BLAS, or you are writing your own pthread implementation of it. So you are trying to make the program faster. You are not trying to give a different output here. So I saw some no, they can't, right? So you can have, this is the one confusing part which you have, that you can have separate CPP H and output files. They can write in, because I have asked you to actually plot this in GNU plot, right? And this thing about the mean runtime and the standard deviation of runtime, this is a very generic thing, that if you, when I'm, anytime I talk about runtime is a function of many things in the system. So you don't just run things once and measure the runtime. You typically run it 100 times, that in a particular for loop you can take for the same input, and then you get some times which are very close to each other. So it might be 10.57 milliseconds, 10.581 milliseconds, and things like that. So these are your the runtimes which you measure in your program, and then you take the mean of it and the SD of it, right? And this is the plot which you plot in GNU plot, where on the x-axis you have your matrix sizes gradually increasing, and you have your mean runtime with a standard deviation as an error bar. You can just Google up what is a box plot with an error bar, right? It's not something which I have to tell you. So this is what I'm expecting, that for each size of the matrix, you will run the program, run your implementation multiple times. And as the matrix sizes increases, I expect to see a change in your runtime, which should typically increase, right? For increasing size of input. And you can have separate plots for pthread. So you can have one plot for sequential, another plot for pthread, a third plot for BLAS, and a fourth plot for MKL, right? And you are free to put your output anywhere which helps you plot these plots. Okay, so don't worry. So here you are actually submitting the plots and in your GNU script, so you don't worry too much about. Definitely, I mean, so again, Sachin will tell you the exact the command line, but it's okay, because here the important thing is you actually save your output into a file which your GNU plot script can read and plot, because this is a plotting exercise which we are giving you. Okay. So in terms of actually getting the input and the output, it should be, as I said, it should be the same as you did in subtask 1. Your outputs can be saved in separate text files based on separate CPP files. You don't have to keep fighting over function names here. Okay, so just dump it in separate files and plot it out. Okay, so and all these CPPs and header files and should be compilable through one common make file, right? So that is the only thing which I'm saying, that you have this like one make file which takes care of how many CPPs and header you have in your project folder. That's the only purpose of your make file, so that we know, the TA knows that which part of your code is lying there.
Hello, ma'am.
Yeah, go ahead.
Ma'am, there is one issue that in Mac ARM processor, there we can't run MKL because I searched in internet also that MKL is not designed for ARM64 processor, and with the virtual machine also we are not able to run in Mac
Fine.
M1
So
ARM.
you just like report that issue. We'll have to distribute the marks in a different way. So this like with x86 and with on both Linux as well as Mac, it should work fine. I don't know how many of you have newer ARM laptops, or rather Mac laptops, which have ARM CPUs. But that is not something which is your fault. That's okay. And the other option is, if you want to, you can access. I can give access on a GCL x86 machine, and you can run your program there. Okay, so you separately ping me on Teams, and I'll let you know
Okay,
if
ma'am.
more
Yes.
people are having this particular problem.
Yes.
Okay, fine.
Thank you.
Ma'am, one more thing.
Go ahead.
Ma'am, while mentioning the library files, suppose my teammate has mentioned some another name, like it was in another folder, and then I change it for according to me. So, ma'am, that will be hard coded in the sense that we will submit. So, will that be a issue that library files are in different folder than which are mentioned in the CPP?
Yeah, so see, even the TA, when he or she evaluates, the library path will be different for her. So typically for these kind of subtasks, you will be showing a demo to the TA. Okay, so this won't happen on February 21st. It will happen after the final deadline, because it's hard to take care of everyone's path, because each have installed it in a different folder. Even all the 10 TAs will have installed them on their machines on some different paths, right? So definitely the same makefile cannot find all of it. So that is that again, don't worry about that. You make sure that under the path you have on your laptop, you have provided the correct path in your makefile, and it is compiling fine and it is running fine. Okay.
So the path will be according our machine, right?
Yeah, the path will be according to your machines. There is no way you know what the path will be on the TA's machine. Okay.
So there won't be any automated running like the evaluation on the TA's part. So it will be just a screen sharing from our machines and they'll be evaluating on that.
So so there will be some automated evaluations, as you can guess, for the part 1, subtask 1, we are doing that. For subtask 3, it will be the pthread implementation, which won't have any path issue. So again, that will be the neural network with lot of keywords, which will be automatically evaluated. Only the MKL and the BLAST parts, so there also we can specify something, maybe /opt or something, that you can, I mean, I think that should be a small change for you. So mostly what the TAs have told me, that they can do a small demo with you. So they can screen share, and just for the MKL and the BLAST parts where there is some installation which is involved. Okay.
Yeah, so for the sub part 2, we don't need to worry about such things. So it will only
Yeah,
be the...
don't worry about the library paths for now.
Okay, thank you.
Okay. So I think most of you, since some of you have done the assignment, I don't know how much of this multi-threading the class is specifically needed. There were some people who said that maybe it will be good to take a class. So generally we don't like go into, so this is like COP 290 is only the class where we use multi-threading. Okay, so we just use multi-threading, but this will keep coming back to you. So for example, there are 2 specific courses, which is one is this COL 380, which is introduction to parallel programming. So this will have 3 to 4 lectures on different threading mechanisms and what goes on there, and definitely the OS course. So these 2 things run parallelly again. So they run at the same time. So both parallel programming and operating systems, they will talk a lot about threads. Okay, so this is so the department says that in COP 290, students should suffer from multi-threading. Suffer in the sense that they should at least use threads, and they possibly will run into some synchronization issues, or they will not understand that though they are having 100 threads, why are they seeing a dip in the performance. So you are trying to get like given a feeling of using threads without actually going through the concepts of what is going on underneath. Okay, but it is very vague and difficult to do that kind of a thing. So I will tell you some things, right? I mean, it's not just so we can't use threads as a black box, right? So this is what is expected of us in COP 290, that just think of pthreads as some black box, and use it in your program, right? So we'll go into little detail of what goes on when we create multiple threads within a program. But these parallel programming and OS courses will spend like maybe half a semester or quarter of a semester just on threading. Okay. So when we create a program. So for example, this CPP program which we have and the header file and whatever we compile together, this executable which we are having, right? So whatever you have called it, let's name it a.out or something. So this, when I actually run it, so when I run an executable, this forms a process in my system. Okay. So here I'm talking about this process because process and thread are kind of very similar things in Linux. So when there is no process, when we just have written the program. So we have written the program, we have saved it, we have compiled it. Till that point, there is no process which contains this particular program. So there is, of course, the whatever the gedit program or the gvim program if I'm writing it in an editor, or there is g++ program. So these are other programs which are running. It's not my program. A.out is still not a running program until I run it, and only when I run it, it becomes a process. Okay, so this process is under control of the operating system. So this is why the operating system class will talk about this in detail, because the Linux is an operating system, or Windows or Mac as an operating system, they handle these processes. There are multiple processes running on my laptop at this moment, and the operating system decides that which process runs, how much RAM the process gets, which process runs now versus which process runs next. So all these are decisions which the operating system is controlling. Okay, so to control these things, so the operating system is also a large program, right? So operating system is also, so Linux itself is written in C++. So operating system has to maintain a lot of data structures regarding these programs, right? So for example, a particular process context, suppose I have a.out as my process, the operating system will have to maintain a set of data registers. So these are all my X, Y, Z variables which my program use. So the operating system has to allocate a set of registers so that these variables can use those registers for addition, multiplication, or other things, right? So there is you might have heard about this. So this is a stack pointer, right? So this is typically in the RAM how things are organized. So some things on my program are on the stack. Then I also have a runtime heap. So in the data structure class, if you have done malloc and or you did it in Java rather. So, but if you have used some arrays on some buffers, they would have been allocated on this heap, right? So these are typically this all stack pointer. This is the program counter. So the program counter is maintained by the operating system for each process. So each process has its own program counter, so that it knows that what is the next instruction to run. So wherever the program counter is pointing, that will be actually taken into the ALU and other processor units, and that is what will be run by the computer. Okay, so this is why am I talking about these things, right? I'm talking about these things because this a.out, when it is a single process, so here it is a single process, so it has one stack pointer, it has one program counter, because this program is just running and there is no confusion about which is the next instruction and or where is the stack pointing to. There is only one instance of this program running. So what happens, so when if I'm looking at it, if you think about this, that when I'm having threads, the thing is there will be one main thread. So there will be one main thread of the program, but a multi-threaded program means I'll have more threads in the same program. So at the high level, I am running ./a.out, but it is not only having one execution thread or something, one thing which the operating system is maintaining. Internally, the number of p threads I'm creating, it will have those many threads of execution. So what does a thread of execution mean, right? So the thread of execution means that this part, the thread, so suppose there is a thread 1, which is the main thread, that has its own data registers, condition code, stack pointer, program counter. Okay, and there is another thread which I have created. This is a P thread. It will have its own data registers, it will have its own stack pointers, its own program counter. So what happens, so suppose I have written a code which says that x equal to 4, y equal to 3, and z equal to x plus y. Okay, so if this was a single threaded program, I would have only the main thread, and then so this is maybe this I call this program for thread. This is some stupid name of the program. So this is a program for thread, and whenever I do this p thread, so I have p thread t, and I say t p thread underscore create. So I have a slide on exactly how to write these things. So I have to create this thread with some parameters, and then I have to pass this function for thread. I have to tell that I want to create another thread of execution along with the main thread with this function. So my new p thread should run this function for thread. Okay, for thread, and then again there will be some null. So this pthread create, I have to pass a particular function which I want my thread to run. And I not necessarily just call pthread create once. So I can have pthread create pthread t1, t2, t3, t4. I can create as many threads that my program needs, or I think that it needs. And then I will have this ampersand t1, ampersand t2, ampersand t3, and I'll create those many threads which I need, which I think I need. And all of that I say, okay, all of them should execute this for thread function. They should start here. But now you see that the operating system has somehow have to keep track of this thing, right? It cannot work with a single stack pointer or a single program counter, right? Because now there are multiple workers kind of which are coming and executing this code. So for keeping track of this is thread 1's local copy of X, Y, and Z. So it has to have its own data registers, the two threads. Then maybe the first thread I have just created, so it is at this point of execution, whereas the main thread, which had originally started, has already reached this line. So the program counter also needs to be separate. So there will be different program counters for each thread pointing at different parts of the program. Okay, so this is where this is why I'm showing you this lower level details of what the operating system does, because unless you think of it like that, you might not understand why some bugs are coming in your code. Okay, so why did, so one particular bug which you might see is suddenly you see you have created many threads, they didn't complete their work, but your program has ended. If some of you have already tried with pthread, this is a very typical problem which happens. Okay, so this happens because the main thread, it has finished and it has exited the program, right? And you didn't ask the main thread to wait for the other threads to join it. So this is again a very important function where we say pthread underscore join. So you say, okay, main thread, you have finished your work, but the other threads which were doing their own work, they haven't finished yet. So you cannot exit the program. Okay. So this is this all we'll check. We'll see what the syntax of these functions are, which are the ones which you will need in your assignment. But at a high level, in terms of learning a new concept, think of this as earlier when you were writing a single threaded sequential program, it created just one process for your operating system. When you ran it, it's like said just / whatever out. It was one process with one set of registers, one set of condition codes, one stack pointer, one program counter. But as you introduce more threads, now it will start having much more context. Okay, so this is the operating system will keep track of all these different stack pointers and program counters. The good thing is some of the things are still shared. Okay, so this is a good thing as well as a bad thing. So some parts of like the read write heap and those things, they are shared. So in that way, it's very easy to like talk across threads, right? Because they are within the context of the same program. So it's not like that some variable X which thread 1 knows, thread 2 has never heard about it, right? So there's this notion of having shared variables within the same program. What is, so we can have some thread local variables, and we can have something which all the threads know about. Okay, so why am I saying that this can be good versus bad? The bad part comes that if I am sharing something, I might introduce some bugs if I'm not careful in who has access to it at the moment. Okay, so I'll come to this this later on. But for this slide, you just remember this, that if you have multiple threads in your program, there are some things which get replicated, like the stack pointer, the program counter. You have it for each thread, whereas some parts of the program are not copied. So there is only one single copy of certain things. Okay. So any question in this part? So this is not really very important in the context of COP 290. There is no written exam here, and all this you will revise again when you go to the OS course. Okay. But still, if you think that something doesn't make sense at all, just raise your hand or ask a question. Okay. So,
Hello,
go ahead.
Can we create variable number of p threads? Like if I get an output from the user like 5, then my program will 5 number of threads.
So you can call pthread create in a loop as well, but you have to be careful with the pointer you pass there. So you can create an array. So this can be not a pthread variable, but it can be an array of pthreads. But you choose your indexes carefully. So it should be like, so you understand it, right? So T index 0, T index 1 or whatever. You can definitely do that. Yeah. Okay. So the second thing is, why complicate our programs, right? So this is always I ask that. So you are asking me, I had a very nice clean program, right? I had one for loop nested inside each other for my matrix multiplication, and at the end of it, I had a nice result with which I added the bias terms, right? This was the structure of my program. And it was running fine. Whatever Sachin sir gave as input and output, it matched it within 3 places of or 4 places of decimal, right? So this is all very good. So threads are not for improving the accuracy of a program. Okay, so threads are not giving me some new accuracy or new utility or something which I already didn't have. So threads are only to do with performance. So by performance, in this case, I just mean that hopefully, so this is a sort of a loaded term that initially don't raise your expectations too much. Okay, so hopefully it will reduce runtime. Okay, so that is why we introduce threads into the program. We have multiple threads dividing up the work. So we have a fixed amount of work. We know that this is the size of the matrix A, this is the size of the matrix B. We definitely have to do this by this and keep doing that. Now we are just saying that instead of doing this sequentially, we first get rid of this and this, and then this and this. Why not we create as many, I don't know how you have divided up the work or how you are planning to divide up the work, but you can just have different threads taking care of the different parts of the computation, right? So we are having and we hope that since we are sort of the whole of thing is parallelizing, right? So we are saying parallelizing or concurrent. These are also terms you will learn in the parallel programming course. So we are saying that if you run things parallelly, then things should finish faster. Okay, but I think it is we will come to this, that why your hopes might not hold in the next slide. So in this slide, I show some experiments from some random experiment I was doing. Just wanted to show that what happens when we increase threads. So here I am working on a GPU machine. So it's something like a CPU, just a different kind of a processor. And here I am doing some processing some images. So I have this unit of frames per second. So frames per second, like you are measuring runtime, you can think of this as FPS, the frames per second is 1 by runtime. Okay, so the higher the lower you have runtime, the more frames you will be processing per second. So your FPS will go up. So this is a throughput metric. So I'm plotting that here. Whereas in your assignment in GNU plot, you will be plotting a latency metric, right? So that is the runtime. So that's fine, but it is something equivalent. And for me, higher is better, right? So always when you plot a graph, you think that should my values, where should my values be? Should I be in this part of the graph or in this part? Higher is better or lower is better? So for me, FPS higher is better. Throughput is higher is better. For you, lower will be better because you are plotting latency. Okay. So here what I'm seeing is I'm increasing the number of some threads. So this ignore this for now. These are threads for the GPU. And as I'm increasing my number of threads, this red thing is my FPS. So I'm having some increase. Then there is some strange phenomenon happening here. I'm seeing a drop, and then again I'm seeing an increase here. Okay. So this is something which is will be difficult to explain to you at the moment, because it has got to do with something with the GPU cores and how many threads I was using. But this can happen. So it's not that whenever we increase number of threads, we will always see a homogeneous increase in performance. Okay, so there can be some other thing playing into the picture. Mostly what we see is we do see an increase. So this is nice. So this is what we are hoping for. But there can be glitches and other things which we have to explain in some way. Why did that happen? Okay, but the more important thing is, why could we do this? Why could we get an increase in frames per second as we increase threads? So this kind of is shown by the blue curve, which is on the this y-axis, this second y2 axis I'm showing you the GPU utilization. So what happens is in this blue curve, as you are seeing, I am utilizing the GPU more and more. Okay, so I am only seeing benefit of using more threads, because with one thread my GPUs were used only 40%. So I have a very powerful processor. I have many processor cores in my GPU. So with a single thread I was able to use only 40% of them. As I increase more and more threads, I am more of my GPU start getting busy, and I am able to actually utilize my hardware resource better. Okay, so this is what I hope will happen on your laptop. Okay, so typically the laptops on which you are working these days, it might be quad core or octa core, and or even dual core, right? So if you have another core, so if we have a single thread in our program, then that will occupy one core, or out of the 4 cores, right? Or 1 core out of the 8 cores. So the remaining 7 cores are remaining idle. Nobody's giving them work. So the hope is that as you increase your number of threads in the laptop, the processor utilizations will go up. So this will be something like this blue line. So this will go up, and as a result of it, your work will start getting finished faster. Okay, so you will also see so you will see possibly a graph like this where your latency comes down. Okay, this is another graph where where each line denotes how many threads I have in the system. not the x-axis. The x-axis is kind of what you have, something similar to that. This is the size of some grids. So I'm processing some matrix kind of thing, and I am on the x-axis. I am saying that how many grids am I processing. So as I'm increasing my number of grids, my single thread runtime. So this is again this is the runtime. So higher is actually bad here. Higher was good here. Higher is bad on the right hand side. So if you can see that one thread is having the worst runtime, right, compared to two threads, and then there are these things here. Okay. So here also increasing the number of threads improves my performance, right? My runtimes come down. So we will come back to this graph again in a while, where I say that why you cannot always expect an increase in performance with threads. Okay. So but you understand overall, right, that we use, so the high level point is your sequential program is perfect in terms of accuracy. Introducing threads, you might actually introduce a bug and reduce your accuracy. Okay, but still we typically use threads to improve performance, to reduce runtime, increase throughput, and this happens because we are able to use our hardware more effectively. Oh, go ahead.
Ma'am, I read out, ma'am, in our laptop it is written it has 4 cores and 8 logical processors. So does it mean we can 8 threads, or do we can run 4 threads, like four cores? Like what is the difference between this?
Yeah, so I think it's similar to what I have here. So this is my yesterday when I was trying checked. So I also have 8 vCPUs. Okay, it's a quad-core laptop with 8. So you actually can check this. So these are some Linux utilities. So you can run your program with different number of threads, and this will show you. So this is my core 1, core 2, core 3, core 4, core 5, core 6, core 7, and core 8. So it is giving me the utilization of this. And since I was not running any program, so I am seeing that this is the percentage idle here. So if you give enough work, I don't know who asked the question. So you should see all the 8 cores becoming busy gradually, right? But again, is so compared to one, so you can try with your one single thread. Forget about the runtime, just check the utilization. All of this should look like, so it should be like only the core which is doing a lot of work, that should show you something, maybe say 40% utilization or something, right? That so that should be 40% idle, because that is being utilized 60%, but the rest of it should be almost idle. And you gradually increase the number of threads, you should start seeing changing numbers here. So you can play around a bit with, and some people might just can have dual core, right? So they don't have those many cores, and there only 2 such rows will be present. Okay. So this is a sample output, and there are, so this is just one sample utility I've used at MPStat. So I mean, you can also do PS or top or other things. I like this utility because it gives this nice separation between all the cores and shows the occupation. Okay, so check this, that how, I mean, even with these utilization, your final runtime might still be the same or worse than what you had earlier. Okay, I'm saying this repeatedly because I have a reason to say that. I'll come to that. Okay, but at least you see whether you are able to use more cores on your system or not. Okay, so try this out, that it should at least occupy more cores. But the thing is, I'll first come to this and then I'll go above that. As you can see here, right, at this part of the graph. So what happens is, if you don't have enough work for all the threads, then they create more tantrum than actually doing something useful. Because I mean, as we are seeing, right, the creating a thread, maintaining a thread, it's not zero overhead. So every time you are doing this pthread underscore create, it is creating a set of it. This particular function call itself has some overhead, right? And then the OS has to maintain all this other things. Then you are doing this pthread join, you are holding back one thread from coming out for the other ones to complete their work and come back, right? This is again another extra additional function call. Now suppose you had too little work, so it just happens like think of it as your teammates, right, in COP 290. So if the assignment is too small, like you just have to write a small piece of code, then it doesn't really matter whether you had one person versus two persons, right? Maybe having two persons and having the number of WhatsApp messages and calls across you to synchronize took away much more time than a single person would have done, right? So this is one part, is very small amount of work. Okay, so don't always expect to see a benefit of multiple threads. Think of whether you can plot it out in this fashion and say, maybe I'm not even having enough work to require those many number of threads. So this is why I asked you to do this GNU plot business, so that you yourself can take matrices of different sizes, and you shouldn't see between your different implementations of sequential, MKL, BLAS versus pthread, the first graph, the first runtime, or even the first two runtimes for two matrix sizes might be very similar across these four graphs. Okay, it is only when you take a significant size of the matrix, maybe you actually see that this is a huge runtime versus this maybe optimized things better, and maybe this other library optimized it in a further better way, and maybe you could actually do an even better job than any of the libraries, right? So, but don't expect to see this difference in performance for a very small matrix size. Okay, so these are all things which you should plot and report and write the report, right? These are all your observations that you think that this didn't improve because of this reason, right? And you can also have take a screenshot of these utilization numbers. You say that see, even though I didn't see a drop in runtime, still I utilized all my cores to a much higher extent than when I had a single thread. Okay, so in your report you can put this utilization numbers as well based on how many cores your laptop had. And another important thing is, don't ask another team for their runtime. Never ever compare, because each of you have very different laptop generations and this thing. So it should only be that the MKL and BLAS and threaded implementation on your laptop should show some trend. So someone else in the class might have like a super fast some latest x86 which has like very little runtime for all the values, whereas you are seeing much higher values. Okay, so don't compare across hardware devices. So that is one thing, the amount of work, and whether the trade-off of overhead of creating threads, maintaining threads versus this even makes sense or not. So that is small amount of work. The second thing, which also I think you are seeing a lot in COP 290, is like that some slow threads, right? So you don't see this all the time, because here you are having very like uniform work, right? So I think when you are dividing up a matrix multiplication task, there is no reason you will give one particular thread 70% of the matrix and the other thread only 20% of the matrix, right? So, and the OS also should not treat these two threads very differently. But it can happen that some thread gets sort of delayed for some reason. There might be something else running in your laptop. So maybe you are doing a class, right? And in the background you are running this program. So maybe T1 has finished its part, whereas T2 has got stuck, and some higher priority thing for your online classroom has come into the forefront. The operating system has delayed this. So this is same as having a very slow partner in your COP 290, right? So you have finished your part of the work. That other partner's family got COVID or something, and that thread is not finishing its work, right? So it also happens in real systems. So when I say this pthread join, I cannot exit the program unless all the threads have finished and I have combined their work, right? So ultimately you need to output this one output file where maybe parts of the file are written by certain threads, or maybe you actually don't want to do that, right? You don't want all the different threads to open a file and write, because it might leave your file in a very inconsistent state. So what you actually do is you have created many threads, you computed their values, but then there is one single thread which copies them into this single buffer, right? So this is a very sequential operation, right? So there is these are all places where your benefit of parallelism might go away. So you had nicely parallelized your program, everything finished under certain things, but finally when you are combining the work of all these threads together and you are writing it out to a file, then all the benefits went away. Because this was essentially, it was like a sequential process where the threads had to wait for each other. So what is the hope here? The hope here is that this parallel part will be much larger than this combining part, right? So we call within a program. So when I have this title as can any program be multi-threaded? So a particular program might have some sequential part where we must do something after the other. We cannot start doing the matrix multiplication before we have read the matrix. So that is a sequential operation in any way. We cannot parallelize those two things, right? And the other part, which is like which we call as mostly as parallelizable part of the program. And the hope when we use multi-threading is this is much bigger compared to this. So even though we have some sequential things in the program, with parallelization or by using multiple threads, it really helped us. Okay, it really helped to reduce the final runtime. So same as your the talking to your friend, right? So you and your friend have a very slow network connection. So whenever you try to do things together, it becomes a mess. But the thing is, most of the time you two can just continue parallelly, right? So you can, and this part is much larger. You have already divided up the work. You told her to take care of MKL. You are taking care of BLAS. You don't have to talk to each other unless you have even finished the GNU plotting and you're just comparing the plots, right? But at every step of BLAS installation, if you have to talk to her, then there is a lot of more synchronization which is needed. So the first thing when you are doing writing any program, making it multi-threaded, you see that how much of it is kind of independent of each other, right? What is the task which you have, which can be split up into things which don't depend on each other. So that's the first thought process. And typically these things like these matrices or images, they are what are known as, like they are called something as embarrassingly parallel. So typically when you have graphs and other such data structures, things are not so easily parallelizable. But typically a matrix, you can break it down into some parts, and the computations just don't depend on each other. Okay, so think through this thing very carefully, that how should you divide your work so that your threads don't have to talk to each other a lot. Okay, so this is an important point, that minimal communication or dependence among threads. Okay, so this the more I have dependence, the slower I become, because I have to synchronize and do those things. So this I didn't want to put too many things, because there are like just read the first pthread tutorial you get, right, on Google, and there are so many of them. So this is typically how things are, that you have this create. And as I say, there is a particular, so whenever you create a new worker, you have to tell the worker what is the work they should do, right? So this is where it is passed, that you say that I am creating a new thread, and actually this pthread create returns a pointer to the thread, which you have to assign to this TID. And so this is what you pass to the function. It will be assigned here. And this is some stupid hello world. So when you are writing your first pthread program, you can start with just a set of printfs in the program, not doing the actual matrix multiplication. Check out the order in which, so each thread just make it print its own ID. So it should print the TID it has, and if you see, you will see that it might be that 3421 4213, so it can print in any order. So that will kind of like give you this understanding that you cannot predict the order in which your threads finish work. It is in the hand of the operating system. You are just creating 5 threads. You cannot tell the operating system thread number 1 should finish its work first, thread number 2 should go second, thread number 3. There is no way to do that. Okay, there is no ordering here. So that is why it is better to give them independent work, and then the OS will mix it up. So thread 5 might finish first, and then thread 4. But typically when you are doing this kind of matrix multiplication and addition at the end, these things commute, right? So 1 plus 2 plus 3 plus 4 plus 5. So I'm when I write this plus, I'm saying that this is the output of these threads. Will be same as 3 plus 4 plus 1 plus. So these are commutative operations, so it won't matter. The order doesn't matter. So this is something which if you start with a printf and every thread prints its ID, it will just get into your head that there is no control for you on which thread finishes first. Avinav, you have a question?
Yes, ma'am.
Yeah, go ahead.
Here, let's say when I create one thread, pthread, like thread ID, and then when I say join, so like immediately after that, before creating another thread, so will that finish the thread's task and then that thread will move ahead, or will it wait for others?
Oh no. So this is the thing that so actually this I have a picture here. So the pthread join is for the main thread actually. So let me this is a good question actually. It brings me to the next slide. So what happens is whenever you call pthread create, a new thread gets created and it goes to its work. So it will, when the new thread which you have created, this will actually go to Howdy. This will not go to this step. So this thread, you say that, okay, I create a new thread, I give it this work, and that new thread will start work from the first statement in Howdy. It will do the printf and it will do a return null. Then only it will go here. It will come here. So this pthread join, why I have put it here, I want, so there was a main thread in the, so here when I had started my program first and I hadn't done the pthread create, I had only one thread in the program. That was my main thread. So here, why I have put the join here? Because I want the main thread to come and wait here. Otherwise, what would have happened is if I hadn't done the join here, my main thread would have exited. So my program would have finished and I wouldn't see the print statement, because by print statement was being done by another worker who had no clue that this program has already exited by the main thread. So why I have put the join here is for the main thread to come and wait here, so that this thread, this T, the thread which I have created, it finishes its work, it does the print, it returns null, it goes back here, and then only the main thread says, okay, this T has, I have made this so dirty, let me just pull up this. So it is only after this thread returns here, the main thread knows that, okay, this TID has joined me. So now it is safe for me to exit. So the join is actually here, the main thread is waiting here for TID to join it. And if you have multiple threads, so that is the way you synchronize things. Okay, so this is a kind of the pictorial thing here, that as soon as you create a new thread, it will not come to the next function call here. It will go to the work you have given it to it, which in my case is this Howdy function with a printf. And only after return null, it goes back to what it wanted. And in this part, till it returns, the main thread is waiting here. So Avinav, is your confusion resolved? So you try this out, okay? You create 4 or 5 threads and you have a main thread and make, so you depends on whom you are waiting for it, you can change the TID. Check whether that particular TID has yet printed or not.
Okay, I have a small doubt. Let's say I have to create 4 threads. Here we have only 1 thread, but I have to create 4 threads. So is it possible that first I create all the 4 threads and then I join all the 4 threads? It is possible, right?
Yes, yes, yes. Think through
Or
this.
do I have
So
to
that
do it,
that is
create, join, create, join, create?
no, 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 no. You don't have to do other. What is the point? Then the program becomes sequential. You are not having parallelism.
Oh, true, true.
Right.
Okay.
So it will be. So think through this. So think through how like you should actually have multiple p thread creates. As someone was asking, you can even do it within a for loop, right? If you have like really I mean I don't so since you are working on your laptop which has maximum 8 cores, don't do this in a for loop. Okay, you can create. Yeah, go ahead, Divyanshu.
So this might be silly doubt, but like we can create a large number of p threads, right? Like up to 100, something like that. But then, so doesn't every p thread create a new thread? So like because we can actually have 8 or 9, like depending on our CPU, 4 or 8 cores, right?
What do you, I didn't get it. What did you say?
Like we have got limited cores, like 4 or 8 cores of the CPU. So like we can run, I think 4 or 8 processes parallelly then according to that. But
yes,
then how can we create 100 p threads like?
Yeah. So the thing is, I mean, even with a single core, when you have a single core, still you can create 100 threads. Nobody stops us from doing that. Okay. So typically why sometimes we do that? I mean, not 100 maybe, but maybe we create 2 to 3 threads because all the time the processor is not used. There are memory functions, there are IOs. So there is, if I have a single thread, maybe my processor is lying idle sometime. So the purple screen which I had shown, right? So if I had a single thread, maybe I see that with one thread, I have only 50% utilization on a single core, I'm saying. So even with a single core, maybe I create 2 threads, and because their IOs and memory reads don't overlap, so there is maybe I can push its utilization to some extent. So it's not always true that we have the exact same number of threads as the number of cores. But I would say that that is what is a good design, that if for you don't create 100 threads. Okay, so there is I don't see any reason. So when I am working on a GPU, I can do that. I do that very often. But if you have 8 cores, you create 8 threads and see what is your using the tool, what utilization you are having on the 8 cores. Okay.
Yeah, okay, ma'am.
Yeah. Srimanti, you have further doubt?
And one small thing, ma'am, can it happen that when we are calling MKL and writing the matrix multiplication is taking more time than our simple matrix multiplication? Because
yes,
of life.
it can happen. Yes, it can. So all these things can happen. So that is why I'm saying that don't expect that maybe after plotting all the graphs, you find that your initial sequential implementation is still the best. Okay.
Yeah.
So
yes,
experiment a little bit on the size of the matrix and other things, because typically it happens that just see that there might be some use cases where MKL or using BLAS makes sense.
Okay, ma'am. Yeah.
Okay, so I'm almost out of time. Just like I'll upload the slides, you can check it later. So it's not only that C++ has threads. Okay, so if you have worked in Python, or if you have worked with Java, right? So there also you have actually threads there, multi-threading option. The thing is, in the operating system, they only understand the p thread. So the Python interpreter, if you look at that code, the Python interpreter internally calls the pthread APIs. So you in Python, you are saying that this is a Python thread, you create multiple of them and stuff like that. But this will be mapped to pthread create calls inside the Python interpreter. Okay. Similarly for Java. So JVM, the Java virtual machine, internally calls the pthread APIs. So here you are working at a very low level. You are yourself using these pthread APIs, right? So you are supposedly you are writing something like JVM or the Python interpreter, which uses very low level CPP libraries. Okay. Check this at your own time. I won't go too much into this because I think you can arrange your program so that you don't need too much of it. So because in the case of the matrix, you can design your threads in a way that each output is created by a single thread. Okay, so it can happen that this particular piece of output, they don't have any, it's not like multiple threads are writing to it. If you somehow have designed the program in that fashion, be very careful. Okay, so this is a variable, and this happens that I mean, when you are trying to do this add, right? So add, when it goes into this assembly instruction, it will be LDR from somewhere, then it will be the add, and then it will be the STR, store back, right? So this is not an addition, is not an atomic operation. So if multiple threads are working, T1, T2, T3, so it might happen that one thread has just finished the load, then another thread comes and again loads the same value. And then at the end of it, you have some inconsistent added value. So what you need to do is you will have to use something which is known as lock. You say that I am locking this output value, and so that no other thread can touch it now. And it is only after a particular thread has already added its the value it needed to write that you release the lock. Okay, so my suggestion will be, don't design your program so that you need locks, mutex, or synchronization. Okay, you definitely will need some synchronization in terms of join or barrier, that you wait for other threads to finish their work. That will be needed, but you should not need that the all threads are writing to the same variable. If you do that, but I mean, I am not discouraging it. If you are doing that, do it correctly. So at every step, keep matching the output. Okay, don't end up with a buggy code. So whenever you are introducing more number of threads, you are introducing this locks and stuff like that, you should just check whether the output is same as the sequential output or not. That should not change under any circumstance. Okay. Yeah, so this is the summary slide. I have to finish because I have a music class. So what should you care about is how to create threads and divide work across them. Okay, so you try to figure out what parts of the matrix multiplication operation are independent, with what work to do. And then you should always match your output with single threaded execution. How many threads to create? Try to use this Linux utility and see whether you are utilizing your processors nicely. Okay, that is one way of checking it. You might not be faster, but at least with 4 threads, you should have more cores utilized than a single thread. Okay. Do you see a runtime improvement, same, or degradation? Okay, don't set your like hopes too much that I'm always going to see 400% improvement in the runtime. And try to explain the runtime behavior with increasing number of threads. So if you are not seeing an improvement, you can say that I am only seeing an improvement when the matrix size is this, because probably the thread creation and these overhead values are too much, or I have a long sequential thing happening at the end of my program. So, and the parallel part is smaller than the sequential part. So I'm not seeing any improvement. Okay. So I will end here. If you have more questions, I'll go to the Piazza once more today. I didn't feel like there were any critical questions, but I'll still answer all of them there. The deadline is 21st now. So you give your minors with peace of mind. Some people have done a nice job. I think only 1 or 2 teams who have finished. And I'm not going to give bonus specifically to this assignment, because it becomes a loss penalty in that case. So someone asked me to do this, that after the final division and gradation, all these things happen, then I give the bonus so that they can get a grade update if they can get that. Okay, so 21st is the deadline for your purpose, and if someone has already done it, then they're free to submit it on Moodle to get some grade boost.
Oh, ma'am.
Yeah.
Approximately how much will the bonus be?
I don't know. I mean, these things just, I mean, don't